In this video, I want to talk about perfect competition and cost curves. So where have we been? This is the second broad module about the supply side, and in the first video we talked about the relationship between scale and market structure. You know, we had market demand, and if there were the optimal scale of operation were small, lots of firms could fit into the market. And that's what we're going to run with today with this discussion of perfect competition and cost curves. So what's perfect competition? Well, it's a market structure in which there are many firms producing a homogeneous product, which is just a fancy way to say that they're all making the same thing. We say that competitive firms are, quote, atomistic. It just means that they're small relative to the market. But that does have a specific meaning for us. It means that their production decisions, that is how much output they produce, has no effect on the price. Now that's a little bit interesting. Think about the market demand curve, which was downward sloping with quantity here and price here. Clearly it's got to be true that, if you were to sort of dump a ton of output into the market, the only way to clear the market would be with a lower price. But here, because each firm is assumed to be small relative to the market, what we're saying is that its output decisions aren't a big enough deal to actually move us along the market demand curve. So that's what we mean when we say firms are atomistic. Next point I want to make, though, about as a preview of the perfectly competitive model, we'll see that profits are possible in the short run, but because firms are free to enter and exit in response to opportunities, there will be no profitable entry opportunities in the long run, at least in the model. Now, taken literally, if you think about what's a context with lots of small firms producing identical products, you might think of a bunch of small farms producing undifferentiated wheat. Here's a pretty picture of something like that over there. I would also say, though, that the model should be viewed as an approximate model for situations where many firms produce similar products and anyone can get into the business. And so, later in the course we'll talk literally about a market structure called monopolistic competition. But the point I want to make on this slide is that the perfectly competitive model, literally it's about firms producing identical things, but it's useful as a set of lessons and metaphors about contexts where lots of firms produce similar things, and as I said, anybody can get into the business. All right. Well, here are a couple of pictures. On the right-hand side, we see a market demand curve. That's what we spent the first module deriving, this relationship between price and quantity, the market demand curve. What we have on the left is the firm's demand curve, and it really is in stark contrast with the market demand curve. The firm's demand curve is a horizontal line. Now, there are a couple of ways for us to think about that. One way to think about it is just to say that the firm demand curve is perfectly elastic. The elasticity equals minus infinity. Now, one way to say that is to say that the firm would get the same price for its output regardless of the quantity choice it made. Another way to say it, though, is if the firm were to raise its price, all of its business would go away. Now, why is that? Well, in this context, everybody is producing the same thing, a homogeneous product. So if you were to increase your price, all of your demand would indeed go away. That's why the elasticity is negative infinity. But, take away from this slide, the firm's demand curve in a perfectly competitive market is just a horizontal line at the market price. What else can we say about a competitive firm? Well, one thing we say is that it's a price taker. Why is that? Well, the market price is out there. This firm has no effect on the price, and it's one of many firms supplying this undifferentiated product at this price. Revenue then equals just the price times the quantity of output the firm chooses to produce. Now, what's kind of interesting, I guess, is that price is not a function of quantity. Of course, revenue is, but the price itself doesn't vary with the quantity of output. Let's define marginal revenue. This will be a useful concept both today and on into the course. Marginal revenue is the change in revenue with a 1 unit change in output. Now here, marginal revenue is just constant at the price because you get the same price for each unit of output you make, no matter how many you make. So here, in this part of the course, marginal revenue just equals the price. The rest of this video is going to be about the relationship between costs and output. I want to talk a little bit about why we're doing that, why we're having that discussion. So where we're headed is toward a model that will relate the price in the market to the quantity that each firm chooses to produce. And this will actually culminate both in the firm supply curve and in the market supply curve. But to get there, we first need to understand how costs vary with output. So that's what we'll be talking about for a while. A few definitions about cost structure. First of all, what we call total costs is equal to fixed costs plus variable costs. Fixed costs, or FC, are those that don't vary with the quantity of output. So no matter how much we make, those costs are the same. They're fixed. The variable costs, or VC, they do vary with output. So think about those as cost of materials and labor and things that we need. If we want to produce more stuff, we need to spend more money. What we want to do is to relate costs to output. And we'll be taking a short-run perspective here, and by that we mean that the short run is a period where some of our inputs are fixed and others can be varied. So the standard assumption is to say that capital is fixed. What's capital? That's machines and buildings, things like that. And we can produce more or less output by varying the inputs that are variable and usually assumed to be labor. Now, there's an intuition, sort of this usual shape intuition that we have about what happens to output as we add labor to the process. And it's going to give rise to the shapes of standard cost curves. So I want to talk a little bit about that intuition just so we understand what's going on. So the idea is that first, at low levels of output with small amounts of labor, as you add workers, they become incrementally more productive. What does that mean? It means, for example, that 2 workers can accomplish more than twice what 1 can do. Now, if that's true, then the cost per unit of output is falling. So in this region that we would define as the region of increasing marginal product of labor, because an additional unit of labor adds more to output than the previous units of labor did, in this region, costs are falling. Eventually, however, additional workers become incrementally less productive. So suppose they start bumping into each other and getting in each other's way, then a 10th worker would add less to output than the 9th worker did. I guess that's an N, than the 9th worker did. But a 10th worker has the same cost, so the 10th worker costs as much to hire as the 9th worker did, and that means that incremental costs are rising. And so that later on region, higher levels of output and labor, is the region of decreasing marginal product of labor. So under these assumptions about how the world works, we get standard shaped cost curves of the sort I'll show you on the next few slides. So here we have a short run total cost curve. On this axis we have output. On this axis we have cost. A couple things to note, even with 0 units of output there's some cost. And what's that? Well, that's fixed cost. And by the way, that's one of the ways we know this is a short run total cost curve. Now, what else is going on here? Well, initially, the slope of this short-run total cost curve is steep. It starts out steep and gets shallower. The slope gets shallower, shallower. The slope reaches a minimum. And then the slope rises again. What's going on here? Well, first we have increasing marginal product of labor, which means that the costs are falling, so the incremental cost of making another unit of output is falling. And what does that mean? That means costs rise more slowly with the additional units of output up to some point. And then, after that point of minimum slope, that is minimum increase in cost with an additional unit of output, the slope starts rising. Where the slope is rising, we have that region of decreasing marginal product of labor. Okay, so the thing you have to get straight is that, if additional workers add more to output, so we have increasing marginal product of labor, that means that the increments to cost are falling. Whereas when you have decreasing marginal product of labor, costs are rising, and therefore the slope of the total cost curve is rising. All right, well, we'll work with that picture a lot. And I want to define some average and marginal cost concepts and show you how they work in those diagrams. Let's start with average cost. So average cost is just total cost per unit of output, or total cost divided by Q. We can see average cost in the diagram we just had, and that we'll have again, as the slope of a ray from the origin to a point along the total cost curve. Let me show you what I mean. So here we start with a picture, and up above it's the same picture we've seen. Down below I want to be illustrating average cost against quantity. So the horizontal axes are the same both above and below. The point of this slide will be to show you that we can see average cost in this upper diagram as the slope of a ray from the origin to the TC curve. Here's the origin, of course. All right, so what are we thinking? Here, for example, is a ray from the origin to some point on the TC curve. This is the quantity of output, and what we're saying is the slope of the ray from here to here is the average cost for this level of output, Q0. Well, what is average cost? Average cost is total cost divided by output. The reason why this is also the slope of this ray is the slope of a ray is rise over run. The rise here is TC, the run here is Q0, and so indeed the average cost associated with Q0 is depicted by the slope, or represented by the slope of a ray from the origin to the TC point associated with this level of output, Q. Now down below we can depict this as a dot. It's some level of average cost, so this red dot here. What I want to do now is consider other levels of output. So let's go to a higher level of output. And what do we see? Well, we see that the ray from the origin to this point has lower slope than the first ray did. That means the average cost for this level of output is lower, and indeed this red dot is below this red dot along the average cost axis. This process continues. We see that the average cost associated with this level of output is the slope of the ray from here through this point, and this slope continues to decline, and so average cost continues to decline. That is, this dot is below this dot on the AC axis. This process reaches a minimum at a point where, at a quantity where the ray from the origin is just tangent. It just touches the total cost curve. So we'll make a fat dot there and drop a line down. Now there's something special about that point. What's special about it is that's the lowest slope that a ray from the origin ever has along this total cost curve. And so the special thing is that that quantity, which is called Q star here, is the quantity of minimum average cost. So if we draw in the average cost curve associated, connecting the dots, we see that this purple line declines, reaches this minimum at Q star, and then rises. Let's define a second cost concept, average variable cost. So that's just variable cost per unit of output, or VC over Q. And remember, variable cost was just total cost minus fixed costs. We can depict variable cost in the diagram as the slope of a ray from this point 0 FC, that I'll show you in a second, to any point on the total cost curve. So here we are. Now, instead of starting from the origin, we'll start from this point. Now, the point of this slide is going to be the following. I want to show you that AVC is the slope of a ray from 0 FC, which is this point right here, to the total cost curve. So, for example, here's some quantity of output. The average variable cost of that quantity of output is the slope of this ray. Now, how does the slope of this ray, and therefore average variable cost for this quantity, compare to the average cost at that quantity? Well, the average cost was the slope of a ray from the origin to that point. Well, you can see that this slope is steeper than this slope, so that means AVC for this quantity must be below AC. And sure enough, down below, we'll say this dot is going to be on AVC, whereas the AC curve that we've reproduced from earlier is purple and it's higher up. All right, we can trace out these AVCs and see how they're declining until we reach this point here. This is the quantity where the lowest slope ray coming out of here is just tangent to the total cost curve. So there's something special about that point. It's the point of minimum average variable cost. If we connect these dots, we'll see a few things. First of all, AVC is below ATC. Second, it reaches its minimum at a quantity below the quantity where AC reaches its minimum. Why is that? Well, think about drawing a ray from here that's just tangent. If you started here and drew a ray that were just tangent, it would be, well, farther along this curve, and in fact, there would be right there. Another point to make is that the difference between ATC and AVC, this vertical distance, is declining. Now, why is it declining? Well, it's because the difference between ATC and AVC is just the fixed costs divided by the number of units of output. So as the number of units of output gets bigger, that difference declines. The third cost concept I want to talk about and illustrate in this picture is marginal cost. Marginal cost is the cost of making one additional unit, and so we can see it as the slope of the total cost curve, or if you're a calculus buff, it's the derivative of total cost with respect to quantity. But this slope intuition is perfectly accurate and fully adequate. So now we're reproducing this diagram, adding one more element. The element we want to add is the slope of the total cost curve as we move along it. So again, the point of this slide is that the marginal cost equals the slope of the TC curve itself. Before, sort of drawing things, let's just talk about it. Look at this total cost curve. It starts out steeply sloped, becomes more shallowly sloped, reaches a minimum, and then becomes more steeply sloped again. So here's the minimum. So let's draw a bunch of little tangencies. Think about what's happening as we move along this curve. The slope is falling, reaching a minimum, and then rising. But a few other special things happen. Think about this point right here. At this point right here, the slope of the TC curve itself equals the slope of a ray from the origin to that point. So that means something special happens there. In particular, the special thing that happens there is that at that point, MC equals AC. Now what is that point? That's the point of minimum AC. So MC crosses the AC curve at the minimum of AC. And similarly, MC crosses the AVC curve at the minimum of AVC. So that's some special features of marginal cost. Let me say it again because I think it's kind of important. So MC is the slope of TC at any point. At Q min AC, the slope of TC equals the slope of the ray from the origin. Hence, at Q min AC, MC equals the minimum of average cost. Now you can make a similar argument about variable cost to get to the argument or to the result that MC crosses AVC at the min of AVC. But the diagram's already a little busy, so we won't try to do that. All right. Well, there's been kind of a mouthful here, but let's talk about what we've tried to learn. There are a few takeaways here. One is that for a competitive firm, the marginal revenue just equals the price. Second point is that AC equals just the total cost per unit of output, and we can represent it as the slope of a ray from the origin to any point along that total cost curve. AVC equals variable cost per unit of output, and we could say it's the slope of a ray from the 0 FC to any point along the total cost curve. MC equals the change in TC with a change in Q, and it's the slope of the TC curve itself. With a usual shaped short-run total cost curve, the marginal product of labor is assumed first to be increasing, then decreasing. This gives rise to an AC and an AVC curve that are U-shaped. And finally, MC crosses the minimum of AC and AVC.